So, this is what is on the, and this was posted a long time ago. Feet
Your
down.
feet.
Oh, sorry. Yeah, jeez.
The first topic that we talk about is like the electromagnetic spectrum. Do you know the names of the waves?
No.
Gamma rays.
Infrared.
Oh wait, yeah.
Infrared.
No, they need to know them in order.
Okay, it's gamma.
Micro.
Micros.
Radio.
What?
Radio.
Radio and then what?
Micro.
Infrared.
UV.
UV, X-ray, violet, ultraviolet.
Visible,
Ultraviolet and then what?
and then visible,
Something.
and then visible
Gamma,
light,
and then gamma.
and then infrared, and then
So
light.
radio waves, microwaves, infrared, UV,
Visible light.
visible light. No. Infrared, visible light, because infrared is just before red.
Red, and
Right?
then it's visible
Then it's
light,
visible
and
light.
then it's UV,
Then it's UV.
and then it's
Gamma.
Yes.
Raging Martians invade Venus using X-ray guns.
Say that
what
again.
is it?
Raging Martians invade Venus using X-ray guns.
Raging Martians invade Venus.
Raging Martians invade Venus using X-ray guns.
Yeah, write that on.
Wait, that's good.
Raging Martians invade
Venus
using X-ray guns.
Too late for me. I'll forget the phrase.
What I use?
X-ray.
Miss Thompson, do you got an eraser?
Just flip it over.
Now, what is the speed of light?
186.
3 times 10 to the 8 or 300 millimeters per second.
We didn't know that?
Yeah.
Oh,
What is ionizing versus non-ionizing radiation? What does one do? What does
it makes them an ion.
removes electrons? So I want to see the fact that it bumps electrons up.
Wait.
And when does ionizing radiation start?
What is it, Tim?
Ultraviolet.
After visible light.
And we have UVA, UVB, and UVC. UVA is the nicest one of them all because it has the longer wavelength, right?
Wait, what do we need to know?
So I'm going through the questions here. What is
Can you repeat the thing
ionizing?
about the ionizing and non-ionizing?
Non-ionizing starts with UV, and they have enough energy to bump off electrons. So they will change your makeup as they bump electrons, and they can be dangerous. They can cause cancer and other things. So we have what types of infrared is mainly what? Heat. And the colors in the cones in your eyes, the colors that are observed in the cones in your eyes are what? Red,
And violet.
Green
No.
and blue.
red, green, and blue.
Wait, then what's the red and the violet?
Infrared comes before red, and ultraviolet goes after violet.
And what's the speed of light?
300 millimeters per second.
Millimeters?
No. Meters.
300.
300 million
Uh,
meters per second, or 3 times 10 to the 8 meters per second.
300
million meters per second.
We have done this before, what element gets oxidized and which one gets reduced, right?
Mhm.
Do all metals rust?
No.
Which one rusts?
Iron.
What happens to the others?
They don't.
They get oxidized, but they make a protective coating, right? Like the Statue of Liberty, right?
Wait, what's up the Statue of Liberty? Oh, just the Statue of Liberty was originally bronze, right?
Mhm.
I thought it was copper.
No, like but it's copper. It's copper.
Copper color. Yeah. It was a
The
beautiful
color of
copper
a penny.
color.
So two real life examples would be the Statue of Liberty.
Wait, so why?
Isn't green?
Redox batteries are a real life example of a redox reaction. Combustion is an example of a real life reaction. A redox real life reaction. How to protect a metal from oxidizing?
Put another metal around it so it oxidizes.
That's higher on the activity series.
So a more reactive metal.
Yep.
What else?
Sacrificial anode.
That's the sacrificial anode, right? So more reactive metal. What else can you do to protect something from oxidizing?
Don't put it in water. take out the oxygen.
So the most, keep it dry. But the other one that most people do is simply paint it, right? When you have something that you don't want it to corrode, you normally paint it. When the paint goes off, then it starts rusting again, right? Electron configuration, everybody knows it now?
No.
Remember that the D block is one less? Because that was the biggest mistake in the pop quizzes I was grading yesterday.
What is noble gas notation?
Noble gas configuration is the shorter version. It's the one that starts with the noble gas right before. And I am gonna take that periodic table and put it up because it's got all the noble gas configurations of every single one of them, right?
Wait,
So-
what?
I guess so.
For the people close to it, they'll be able to look at all the noble gas configurations because they're written in every single one of the elements. Yes.
So the beginning of the nobles, or the beginning of the electron configuration, like the complete one, is like the same for every.
Everything. That's the reason that we do the shortened version because everything is the same after the noble gas,
Okay.
right?
Do all metals rust or only iron?
Only iron rust. It's the only one that just completely falls apart when it gets
So
oxidized.
why don't other ones?
They have an oxide layer and it protects them. So, it doesn't fall apart.
How is the Statue of Liberty an example of that if it's copper?
Because it used to be copper and the copper got oxidized,
No, it's
right?
green.
But
And
they,
now it's green.
so it now it's green.
So it didn't rust, it just oxidized.
It oxidized,
Okay.
but the oxidation is a protection. And they wanted to actually polish it and paint it until they realized that you know how many times they would have painted it by now? It would be no Statue of Liberty. Noble gas notation. Do we know what? We don't really need to be recording this.
Yes, we do.
Evaporation and condensation. Do we understand that graph 100%?
Latent heat sensitivity.
So you need to be able to not only understand the graph. You know, this is a much greater latent heat. Why? This is a much shorter latent heat. Why? Understand how to calculate the sensible heats. Understand how to calculate the latent heats. Be able to calculate it from any point to any point just with water. We're not gonna use anything else, just water.
Can you give us the formula for that again?
Q is equal to MCAT, MC delta T.
Can you write that on the board?
Q is equal to M times the heat capacity of water times the change in temperature for the sensible.
What is the heat capacity of water?
You need to know that too.
What is it?
4.18.
4.18, what are the units?
Joules
Joules over grams.
Degrees C. And what if it's in calories? How much is it? 1 calorie per gram degree C, which means that if you have 1 gram of water, about a milliliter, it's gonna take, if you have 1 calorie per gram degree C, it says if you have 1 gram of water, it's going to, in order to change 1 degree, it's gonna take 1 calorie of energy. And the calories that we use every day, like when you say food has so many calories, those are literally kilocalories. And they were determined by burning them and figuring out how much energy they give off, yes.
What is 4.18 joules per gram per?
That-
What is it?
The heat capacity of water.
What is CP?
The heat capacity of water at constant pressure. So, but we don't have to worry about the P because it's all gonna be at the same pressure. We're not gonna be pressurizing and depressurizing containers. It's just gonna be like here, right?
It's 4.18 joules per gram or 1 calorie joules. Or
No,
1 calorie
joules
per gram.
It's
It's 4.18 joules per gram degree C or 1 calorie per gram degree C.
But isn't
So a calorie is 4.18 joules.
Wait, I have something else written down.
I have 4.18 for like liquid water, but like for
For water as ice or vapor is half of that. So it's 2.09 or 0.5, right? And we only need to know it for water, so as long as you know that, but you do need to know those because everybody knows them. Everybody knows them. What does a large heat capacity mean?
It takes more heat to change.
The temperature.
What's the thing for heat?
So if I have, excuse me, so wait a minute. So if you had What has a low heat capacity? Something like a metal. Somebody's gonna get showered today. So if we have something like a metal, somebody was falling asleep. So if we have something like a metal, do you think it's gonna have a large heat capacity? Like aluminum, does it have a large or a small heat capacity? Small. So if you heat up aluminum, it gets hot immediately. And if you take it out of the oven and you have that aluminum foil on top, after a few seconds, it's already cool. So it gains heat very quickly and it loses it very quickly. Very small heat capacity, right? On the other hand, water, you heat it up, it takes a while for you to get it really hot. And then when you remove it from the stove, it takes a while for it to cool down, right? So that's a large heat capacity. It's able to absorb a lot of heat, but it changes temperature slowly, which is great for us. Why? Why is heat capacity of water being so large good for us? Because we need to keep our temperature at about what temperature?
98.6.
Plus or minus 1 or 2 degrees, right? If we change that, then we either get too cold and we can die, or we get too hot and we can die, right? So
Why
I
are some
think
people like hotter than like? Why are some people's like temperatures different than others?
everybody is around the same temperature. Everybody has to be around. Some people may be slightly off, but nobody's gonna be. 99 is fever for everybody. I don't care who you are. If you have 99 degrees, you have a low grade fever. You have 100, you have fever, period, right? You have 104, you really need to be taking something. Actually, the doctors say after 1 or 2, that's as far as you can go. Anything past 1 or 2, you need to start taking something. Is it good for you to have fever when you get sick?
No.
Why do you have a fever?
Because your body's trying to kill the virus.
Oh, is it trying to get so hot that the virus dies?
Yes,
Then why would you want to get rid of the fever?
you don't. That's the worst thing you can do. If you have fever, you need to give your body at least 24 hours so that it can fight it. Unless it starts skyrocketing, which has never happened. I have well, I never did. My kids are already too old for that. But I never gave the Tylenol. And around 1, 2 in the morning, the fever always broke. They always took about 1 to 2 days, and then they recovered super quick. They were never out of school for more than a day.
That's terrible.
No, if you go to a doctor in Alabama, in Birmingham, or you go to a doctor in Columbus, Georgia, which is where I came from, my daughter was 3 months old, and she was running it was like 101 point something, but she wasn't very happy. And I was going to sleep, and I was afraid because people say, oh, it can skyrocket. So I kept calling the doctor, and she told me, if it's gonna make you sleep better, give her the Tylenol, but she doesn't need it. They don't let you give them because then you kill the capacity. The body's, like what you said, the body's trying to fight it and you immediately kill the opportunity. So you're gonna be sicker longer because your body was not able to fight it. Eventually it'll fight it, but it's gonna take longer. Your body's trying to cook it. It's a real, now if it lasts more than 2 days, at that point you need to take something. It's not a good thing. That's what they used to tell us. But talk to a doctor and you'll see that the doctor will tell you, do not give do not give Tylenol at the first sign of fever. You shouldn't. You need to let your body fight it out. Even when I got COVID, I waited definitely a day. I'm like, I'm not gonna take it. I'm not. The second day I was so miserable, I did. First day, you just let your body try to do what it has to do. You sleep, you drink lots of water, you rest. Some doctors actually believe that to help your body, and I believe one of my daughter's friends, her father used to put on her daughter a leather jacket. What? So she went to this thing and she had a leather jacket on because she was helping the body to cook up that virus. I don't know if he was right or not. He may have been completely out to lunch. But I remember she came in the middle of the summer in Baton Rouge and she had a leather jacket on, and I'm like, what are you doing? Now, if you happen to have a fever and your temperature does start going up really fast, what should you do?
Take a Tylenol.
No. Well, sometimes Tylenol will take a few hours to work. So if your temperature starts going up, what should you do to lower your temperature?
Ice.
Cold. Yeah.
Cold water. You get into a shower when you are, or you put water. You put into your bath ice and water. You have to cool yourself. Period. If it starts going crazy high, you have to cool yourself. If you are like in the army, they have ice jackets. that you can put on, so that they can take care of that really quickly. If your temperature starts going crazy, it doesn't happen. I've never known anybody who this has happened to, but it does happen. So I'm not gonna say it does not happen. It has happened. People have gone to 104 like this sometimes. Most of the time, your body, I'll tell you because I never gave them Tylenol. It took about 1, 2 in the morning for both my kids, and around that time, you'll start seeing the temperature go down. And then they wake up the next day and they're fine. So they are not out of school, they're not sick for as long, and your body gets a workout. Talk to your doctor, I'm not Dr. Janet, that's for sure. But okay, enough of this. So high heat capacity means that you can hold on to a lot of heat. So if you have you know how we have pizza stones and we also have, sometimes people use aluminum? Which one is best if you wanna cook a pizza well? Because they have a larger heat capacity. So it's gonna take longer, and they tell you to preheat your pizza stone, right? Because you're supposed to it takes longer to heat it up, but then it will hold on the heat, and it's gonna hold it on more evenly as well. When something gets hot, really fast, it may get spots where it got the heat, like if it's on an element, and those spots will get burned, right? So, but in a pizza stone, things won't get burned in the spots. It's gonna be more even because it has a higher heat capacity. Large heart capacity, look at that. Lewis dots. That's one thing, that's the reason I may move the quiz to the next day. I don't think we're ready on Lewis dots.
We're
100%.
not. I'm so bad at them. I cannot.
You should
Yes,
move it to
so
Friday.
we are gonna leave some time in class today to be working on the master in chemistry, and I may just have a day of just doing Lewis dots and molecular
Can you
geometry,
please?
and that's the topic that I have kind of not gone into as much detail on, so that's the reason I may move it. And then heck, I'm moving it right now, and there are some problems in here, but I don't think this is enough. We really need to make sure that you feel comfortable with mastering chemistry, and some people are struggling with it. Buffer solutions. What is a buffer solution?
Something that resists pH change.
And how do you make a buffer? So yes, with acid and its conjugate base. And what happens if you put a strong acid on a buffer?
It's water.
It'll overpower it and be acidic.
Oh no, it'll create more the conjugate. Wait.
Yeah, nothing happens.
Wait, what was
because
that?
it's
Why would
water.
you put a strong
So-
acid in a buffer?
So if we have,
If you put the base in, it makes water. But
if you have a buffer, the only one we've talked about is vinegar, which has a pH of about 7.4, I believe.
Wait, isn't that more basic? Wait, yeah.
4.7.
Yeah.
So you have a weak acid, as AB was saying, and you have a conjugate base. That's how you make it. How do you put a conjugate base? I know how to put vinegar, right?
AC one.
How do I put an AC minus? How would you make it? Because if I have to put vinegar, I just grab a bottle of vinegar and pour it. Done. How do I pour the AC minus in order for me to make the buffer?
You have to put in an acid to take the A.
I'm just making the buffer.
It dissociates a little bit.
So little is at this point is insignificant, right?
It's supposed to have the same number of AC minus.
Yeah, so how do I add that?
Like put it on the side.
No, in real life. How do I add it?
The dropper.
Put it in a base.
So I need an AC minus. What dissociates when you put it in water?
NaOH.
Salts. NaOH, but that'll give me NAs and OHs. I don't need that. I need sodium acetate. Anything that has NaAA, right? So it's a salt that has the acetate in it, like sodium acetate. When you put it in water, you think it's gonna dissociate?
Yes.
Because it has an A, right? And it has acetate. So the acetate is gonna come in. What do I care about the Na? No, that's your spectator ion. So when I add that, I'm literally just adding a whole bunch of AC minuses. The Na is gonna be there doing nothing, right? So now I have that. What happens if I add an acid to it?
You make more HACs.
I make more vinegar, so the pH is gonna lower a little, but not enough. If I add an OH, what happens?
Water.
You're gonna make water. And that means that you're making AC minus, which is gonna raise the pH a little, but Normally it's plus or minus 1 of the normal pH of the acid, right?
Wait,
So the buffer solution will stay plus or minus 1.
why did you
of that.
add the AC minus if you're just gonna make more AC minus?
I added I added OH, NaOH.
Right, but then why did you add NaAC?
Oh, because I wanted to make a buffer. In order for me to have a buffer, I have to have a weak acid and its conjugate base. And I didn't have any conjugate base. So in order to
Okay.
put a conjugate base, I add a salt that is gonna dissociate, and that's gonna be my source of ACs.
So you had to have the weak acid and its conjugate base before you can put the
That's the
acid in
buffer.
there?
Yes,
Okay.
that's the buffer. Because if I add an acid, the acid will cancel that, right?
Mm.
And if I add the base, and again, how do I add the base? I add NaOH again. I add another, in this case it's a strong, but it's going to dissociate. So I'm adding NAs. Again, who cares about DNA? It's going to be NaA, it's always going to be a spectator ion. They're not going to do a squat. What I'm really adding is the OHs that go over here, right?
If you add NaOH, it will make water.
It will make water. The OH will meet with the H, right? And it will neutralize it and make water, but it will leave the AC minus out. If I add another OH, I just made another water molecule and it left the AC minus out.
What does the AC minus do once
It's a
out?
conjugate base, so it's gonna raise the pH slightly, just not very much. Not very much because it's a weak base, right? This okay? The pH of blood should be how much did they say?
It's
Everybody talked about it.
7.4.
7.4, and it cannot, based on
If
you, it
before
shouldn't change any
7.
more than 0.4, right? Plus or minus, how much did you get?
If it drops below 7 and if it goes above 7.8.
Okay, so about 0.8 degrees total range. So, which is about what a buffer is. It's plus or minus 1. So that's a little tighter than what a vinegar buffer will normally work, or the buffers that we make are gonna work. Excuse me?
Can I use the bathroom?
No. So now we have acid-base titrations. Do people understand those?
Can you
Can you remind me?
Yeah, just remind us.
So in a titration, we have videos on this.
It's okay.
Wasn't that Darren's presentation?
That's one we couldn't hear.
Have we seen? Oh yeah,
And then he said Zach.
Zach. That's what everybody's gonna remember for the rest of their lives.
Is that the VBMB,
Yes.
what?
So that is when we have. I have an acid in here. I have no idea what the concentration is. I'm gonna draw it because I have to draw it. I'm not drawing the CLs. This is hydrochloric acid, right? I don't know the concentration. I can draw or not the CLs because again, they're spectator ions. Who cares about that? At the beginning, we're gonna have an indicator in there, and the indicator is going to have the water looking what color? If I have an acid, bromotamol blue is what?
Green?
No.
Yellow?
So at the beginning, the water is gonna be yellow, right? And then I'm gonna drop some sodium hydroxide that is gonna dissociate. All I really care about is the OH minus. The sodium, we don't care, but it's gonna be there, it's gonna fall as well, and it will be in there swimming around. But the OH is gonna neutralize this one. Now that becomes water. Is it still yellow or did it change to any other color?
It's green.
We have an acid in there.
Oh, it's still
It can
acid?
change, right?
Oh.
Because I dropped one, but those 10 milliliters that I dropped were not enough to change the pH, right? So I'm gonna drop another 10 milliliters and then I'm gonna cancel the other OH. Now what happens?
Now it's green.
Now the water turns green. How is that called?
It's
That's called the end point, which is when it changes color, which we want it to be equal to the equivalence point, but it's not always the same. It should be close. And the equivalence point is when we do what Anna Kate was talking about. when we do the number of moles of the base, so whatever number of moles are dropped, have to be equal to the number of moles of the acid. So for every OH, I'm gonna have an H and I'm gonna neutralize it. When I neutralize everything, then they are equal, and we can use boom boom for the acid, because that's the number of moles, is molarity times volume. You make them equal to each other. We know how much we drop, so we know the volume. We know the initial molarity, because you have to have a known molarity. We know how much liquid we had originally, because we put it in there. We can measure this. So we can find this molarity really easy. You can find the molarity of the unknown. So that's how you use titration, is to find the molarity of an unknown.
You have the volume of the amount dropped, and you have the molarity of the amount dropped.
Yes, because I have to have something that I know everything about, right? I have to have a base that I know its molarity, and I'm gonna measure how much I drop. So I will have both of those. And that's how I know when I drop the exact same amount that neutralizes this, then we know the concentration at that point, right?
Is the base blue and an acid is yellow and neutral is green?
For bromotamol blue.
Yeah.
Just for bromotamol blue. There are other indicators, and this is actually not the best indicator to use, because it's really hard to get that green. So you can miss it easily.
Do we need to know the colors for the?
Yes. 'Cause we've
Only
been talking-
bromotamol blue, right?
Only bromotamol blue, yes. So,
Acid's yellow, base is blue.
neutral is green. Equilibrium and Le Chatelier. I think all of you were the ones who talk about making ammonia, right? So, do we understand that?
No. Well, it's just dynamic equilibrium.
No, dynamic equilibrium is a different, well, yeah, of a chemical reaction, yes.
Can you touch on it just for a sec?
So you can change pressure, volume, concentration, or temperature, and you need to see how that
Is it
change.
EP equals an RT? Like, is it just like saying that if one rises, the other will decrease?
I'm not BP equal NRT, you're talking about gases, ideal
Yeah, but like,
gases.
is it the
With
same,
increase in
like,
pressure, you
ideal?
have more product. Increase in concentration.
It's
reaction
not an
makes more
equation
product.
per se, it's a reaction, so you don't have variables that you can,
But volume, pressure, moles, temperature.
but they are not based on numbers of variables. I mean,
What are we doing right now?
this.
It's
so-
maze. It's equilibrium.
So if we have H2 plus N2, which is who is the famous guy that made this reaction, which I don't like him at all?
Chatelier.
Not at all.
Hager?
Why don't you like them?
Because he's an evil person.
Why?
Why? Because he made something else.
Because the only reason he figured out how to make, you see, ammonia, if we have HAC, if we have vinegar, and we put it in water, it's gonna turn into very little H's plus AC minuses, right? So this reaction is mainly reactant favored, right? If you have vinegar in water, it's gonna be very little H's and AC minuses. It's reactant favored. If we have HCl in water, it's gonna be mainly product favored. Some little bit may go back, but it's going to be mainly product favored. So H plus plus Cl minus. This won't stay. That will just break apart, right? So that's reactant favored, that's product favored. This particular reaction that we have here is reactant favored. That's why it was so hard to make it happen. It's not thermodynamically favorable.
Why?
Yes, in nature we've realized that it's not thermodynamically favorable, and I can tell you why as well.
No. Yeah. Can you say that?
So some of the reasons is that how many moles of gases do you have?
4.
4. And here you have two. So if some of the things that we can change.
So it's like 3H2.
Yes. So you have 6 of those, right? So in order for us to make this reaction go in this direction, what do we need? If we decrease the volume, what do you think is gonna happen? If you have 4 molecules, so you have 3 hydrogens, you have 1 and 2, and here you have 2 of these ones.
We need heat.
If I were to, these are all in the same container, going back and forth, right? If I decrease the volume, what's gonna happen? Is it gonna tend to make more of the less, or it's gonna have to make more of the more?
It's gonna make more of the less.
Right? So if I decrease the volume, I'm going to shift to the right, which means increasing the pressure. These two go hand in hand, right? You either decrease the volume or increase the pressure, which is what he did. He ran it at really high pressures in order to force it, but you need a really high pressure in order to force in this direction, right? We only have 1 atmosphere at real life, and it's not, I think he had like 200 psi, so you really need to stress that equilibrium.
I don't understand why if one goes down, it's gonna shift more than it's gonna shift.
So if we are all running around, right, and somebody puts us really close together, some things are just gonna combine, you know, in order to reduce some of the stress that was just put in you, right? But if they open up, then everybody's gonna separate again, right? So the universe favors disorder. The universe favors things being apart and randomness, right? That's what is favored by entropy, is disorder, right? So things like to be all separate. However, if you put a whole bunch of pressure, they're not gonna wanna be separate. They're gonna try to mingle in order to reduce some of the pressure of pushing you in every direction, right? So they will mingle in order to reduce some of the stress that is being put on you. So if you have more molecules here and less molecules here, you are gonna go on the direction that has less molecules or less moles of molecules. It doesn't matter, same way.
So the name of the famous reaction is called the Haber?
It's Fritz Haber, yeah, so it's the Haber process. He's German. His name was Fritz Haber.
So it's the Haber process is what makes ammonia?
It's how we learn how to make ammonia, and because of that, because of that we have more people on Earth. Because of him, because we are able to fertilize plants and we're able to have more food. Without him, we will have less people on this earth.
Yeah, why is it?
Because the only reason he did this was, he didn't do it to save the world. He did it to kill people in World War II and make explosives. Because ammonia is also used to make explosives.
Oh, he's German?
He's German.
How do
And
they make the gas chambers? Like what gas?
I think it was chlorine gas.
It
Like,
was.
It's one of
how
those.
do they just like?
Well, that's another thing. And his wife got so mad with him because she was also a chemist. She committed suicide because she didn't believe, all he wanted was money and power. And then he won a Nobel Prize. Are you serious? And we're studying him to this day, and you have to.
He won a
But he
Nobel
also,
Prize for killing people?
no, they don't mention that in the Nobel Prize. They just mention the fact that he helped famine because he was able to discover this fertilizer. Now, some people are saying, well, we will have less people, but we will have what we need. The problem now is that we use fertilizer so much that we have put ammonia in our rivers. We have put ammonia everywhere, and it's ruining the quality of our lakes, our rivers, and many others.
What about for temperature?
It's a bad thing. Temperature, this is an exothermic reaction, so it gives off heat. So that's like a product, and what I like to think is like having a seesaw that has little balls on it, and it's at equilibrium. When it is like that, it's at equilibrium, kind of like vinegar. It's at equilibrium when you have mostly vinegar and very little of the others. What happens if you raise the temperature? If you raise the temperature, it will go on this side, so this will go like that. What will happen to all the products? They're going to make in
But
reactants.
if you raise the temperature, it would go the other way.
If you raise the temperature, it goes into that direction, right?
If you raise the temperature on this side, it's gonna be heavier, so it would go like that.
Yeah.
No, you raise the temperature, it's gonna
Okay,
go
well
to
then
that
don't
side.
use the seaside metaphor.
Don't
use
use-
the seaside
don't
because that
use
doesn't
the
make
seaside.
sense.
No, it's a slide.
It says slide then don't call
It's
it
a slide.
seesaw.
Okay, a slide. That's two different
Slide.
things. Because if a slide goes up, then it goes down. But if it's a seesaw, then it goes like this.
Well, this is what I'm talking about. So if I have a whole bunch of little balls and I raise the temperature, it goes in that
Because it
direction.
breaks them apart.
So then what happens?
What?
I don't understand.
So it's gonna shift, if you raise the temperature, the reaction is gonna shift to that side. So what he had to do was to do what? In order to make it happen?
Lower the temperature.
Decrease the temperature so that it will make more of what he wanted. Which was a little bit of a catch-22 because at high pressure you normally have high temperature, so he had to cool it really quickly, like try to cool it in order to force it in this direction. Yeah, pressurize it and then use water jackets and cool it and also use a catalyst. So it wasn't quite that simple. But he did have to cool it.
For concentration, would it shift to the right? If it
For the
increased?
concentration, it's the same thing. If I add more hydrogen, that side of the slide is gonna raise and it's gonna go in that direction,
So
right?
it's gonna go to the
Whose
right.
project was surface tension and viscosity? Oh, Marshall's.
Whose was it?
Marshall, that's the next topic on the thing.
Okay,
What is electrolysis?
electrolysis. So
That's
electrolysis is what we use in order to break water apart, but it's also used to break many things apart. So what I like to talk about, do you understand galvanic cells?
What is that?
Wait,
Batteries?
carbonic?
Wait, can we go in order?
Can we go in order? Miss?
We didn't
Electrolysis is
watch all
last.
those videos.
Wait,
where
can
are
we? We're
We're
on surface
equilibrium.
tension.
Surface tension, what is surface tension?
It's like the skin.
And it is because water, if it's in the middle, like right here, water is hydrogen bonding with everything and attracting everything that is next to it, right? In every direction, water is attracting things. But if you have water in the surface, then this water in the surface is only attracting things that go below because it cannot attract things that go up. So it focuses all this attraction towards down, and it will attract the one that is next to it, right? It attracts the ones that is next to it stronger because it doesn't have the attraction from the bottom. And what happens is it creates like a layer that is going to be denser because it's gonna attract, there's gonna be a greater attraction to those things that, since you cannot attract from the top, it's gonna attract everything down and to the side, right? And it will make a sphere if it can, because that's down and to the side will make a sphere, but if you're in something like this, you'll simply create a layer that is stronger, and that's surface tension. Viscosity is what?
Like when it's thick.
What?
How thick something is.
Resistance to flow, right? How do they measure it? They put something like a burette, and they put water, not a burette, it would never be like a cylinder, right? And they put water and then they drop a little pellet, and if the pellet goes really fast, it's not a lot, very viscous, right? If they put it with honey and they drop a pellet, what's gonna happen? And that's how they measure the viscosity of things, how fast it takes for the pellet to go through that liquid that you have in there.
More viscous, like syrup is more viscous or less viscous?
More viscous. Because the pellet will take longer because it's resistance to
Takes
flow.
longer, it's like thicker.
Yes, it's about resistance to flow.
If it drops really fast, it has a low viscosity.
Yes. Now, if you have the Bohr model, so what we talked about here is how like something, the one that I like to talk about is sodium. So sodium has 11 protons and electrons, and it's 1s2, 2s2, 2p6, 3s1. If any of these electrons jump to a higher level, you could end up with a 2p6, 3s2, or you could end up with a 2p6 and then 3s 3p, and then you end up with 1 over here. If something jumps to a higher energy level, then whatever jumped to the higher energy level at some point is gonna fall. So these are your energy levels. So if it jumps from here to here, when it falls, it's gonna emit a certain amount of energy. If it jumps from here to here, when it falls, it's gonna emit a certain amount of energy. That amount of energy that it releases, if this is the frequency of red, it will be the red color. If this is the frequency of yellow, it's a higher frequency. Actually, I wrote it wrong. It has a higher frequency. That's the frequency of yellow that jump backwards down, so it's going to be yellow. But it has to do with electrons getting excited and then jumping back. And they have to jump in discrete levels. They cannot just like halfway jump up.
Sodium is yellow, right?
Excuse me?
Sodium is yellow.
Sodium is yellow.
So does the kind of wavelength like depend on how much energy it has?
Yes.
So if it has like a lot of energy, it's gonna be like a gamma ray. But if it doesn't have a lot of energy, it'll be like a radio.
Normally light won't get you to gamma rays, but sometimes it'll get you to infrared. You know, infrared, everything has infrared. When you shine light on something, everything will get hot, right?
So the most energy is gamma, and the least is radio.
The least is radio.
Okay.
Yeah, but in this case, we're talking about infrared through ultraviolet.
Oh, so that's not gonna be like radio microwaves.
No.
Okay.
Well, Miss Thompson, after yellow, does it go to green?
It's Roy G. Bibb.
But where'd the orange go?
Roy E. Red, orange, yellow,
So does it like skip?
green. Yeah, orange is a mixture of two colors. That's not a.
So does green skip too? Because green's a mixture of yellow and blue.
Red, orange, yellow, Roy, green, blue, indigo, violet.
Miss Thompson, do we have to know what color is each element?
No, eventually we'll actually look at the colors and things like that, and we'll try to memorize them.
Hydrogen is red.
Hydrogen, yeah, you always say that. Did you see them in physical science?
No, I didn't take physical science. I'm just smart.
I'm just smart. Okay, now we're gonna talk about the galvanic cell, which is the battery.
Is lithium orange?
Lithium is pink.
Do we need to know that?
Is
No.
potassium green?
Potassium is violet.
How do you
It's
know?
not Roy G. Bibb because it skips all the colors.
It's
It's
no. I mean, every frequency, every color has its frequency.
How do you know?
Because you do these experiments in which you get metals and you put them under a flame, and after doing it for so many years, you
We're
memorize
not
them.
supposed to know.
No, not at this point. Eventually, we'll do the experiment and we'll.
sodium is yellow.
We just need to know that sodium is yellow.
Like, what's that called?
This is the galvanic cell.
Can you spell that?
Galvanic or voltaic?
Is this the video we didn't watch?
I don't know.
Yeah.
You didn't watch the galvanic.
Galvanic or voltaic cell. So you have zinc, and then you have copper. And this is the one that I always have one that I memorize. And they're put in solutions. So your zinc is this one. And what is zinc called?
The sacrificial.
So this is going to be your anode. That's where oxidation is gonna take place. And the copper side is gonna be on your cathode. And that is when reduction is gonna take place. We normally, if you had zinc and copper and you join them, zinc is more powerful. That's like your King Kong. It's gonna give electrons to copper. And what we do in order to use it in a battery is we not only connect them, but we also put a light bulb and force it to go through the light bulb.
Wait, so
No.
this is a battery that we're doing?
Yes. A galvanic or a voltaic cell is a battery. And then we put a light bulb. And we force the electrons to go through the light bulb in order to go to the other side. And then we connect it to the copper. So zinc has how many electrons that it wants to lose? 2. So these 2 electrons will come over here. What happens to metals when they lose their valence electrons? They can go into solution and have noble gas configuration, right? So the zinc 2 plus is gonna go into solution. We're still gonna have a solution of zinc nitrate. And normally we put this one in a solution of copper nitrate. So this one has zinc nitrate, this one has copper nitrate. Now, so not only it wants to give them to the copper, but we also put it in a copper nitrate solution. So not only do you have copper, which is weaker, but you have copper 2 plus, which will be able to even give the electrons a lot faster. So the electrons come over here, run through the light bulb, turn it on, run through the computer, turn it on, run through whatever the battery is connected to, because you force them to go through it. If there was a path over here, it will skip the light bulb, right? But it doesn't have that path. It has to go. We use the battery and we take the path away and we force it to go through whatever we want it to go through. And then it gets to the other side. When the electrons get to the other side, they are going to be, the copper 2 is going to get attracted to them. And then the copper 2 is going to do something that it does not want to naturally do. It's gonna become back solid copper, which is not what it wants to be. It was really happy over here, but because the electrons were pushed, now you are gonna end up, this side with time ends up being fatter and bigger because it gains copper, 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 copper. And this side with time is going to lose mass because the zinc keeps ramping into the solution and losing electrons. So that is the sacrificial anode for that reason, because it starts going away, and it's not too sacrificial because now it's very happy. Now, the part that is complicated to understand here is that we have to have something that we call a salt bridge, which literally is just to balance the charges. This side has to be negative, and this side has to be positive for the electrons to want to travel from here to here. Gives electrons, receives electrons. But every time you have a zinc 2 plus jumping here, you're making this side slightly positive. So the salt bridge closes the circuit by balancing the charges. It is gonna send something like NaCl, in this case the Cl minus, is gonna come here and balance the extra charges that are jumping in. And here, every time you take out a copper 2 plus, you start becoming negative. So the salt bridge is gonna send you an Na plus to come and balance the charges. So in the salt bridge, the anion goes to the anode, and the cation from the salt goes to the cathode to balance the charges so that the battery does not become positive here, because then it'll stop, or it doesn't become negative. You have to go from negative to positive. This is balancing those charges.
What's a cathode? What does that mean?
A cathode is the part that receives the electrons. It has a positive charge, so it's where the electrons go. So if you have a battery, your battery is gonna have a negative and a positive side. The negative side is where the electrons leave from, and the positive side is where the electrons go.
So the anode
The anode will be your zinc,
loses electrons?
which loses the electrons, and the cathode, the positive side, is gonna be, in this case, your copper. So zinc has to be, in the activity series, have to be higher, but in the another series that we're gonna talk about later, it's gonna be actually lower. So this is your galvanic cell, and things are going exactly how they want to, from negative to positive, and this is thermodynamically favorable. This is what we have in here. We had salt water, and we had two metals. We had two metals, right? One was zinc and one was copper or something else. I don't know, it came from China. But they did have two metals that were dissimilar, and I connected them to this motor, right? I connected one like this. We may be able to put them back together, and one like that. And then what happened? The electrons started going from one side to the other because I don't feel the voltage. The voltage is what causes this to happen. These two metals feel the voltage, and because they are connected through the motor, the electricity started passing through and ran the motor, and my little saltwater cars were running, which is pretty cool to see. They don't have a battery. There is no battery here. There is nothing here except two metals, one giving electrons to the other, and we are forcing them to pass through this. And then we have the salt water car in the middle. It doesn't last for a very long time because it's not divided the way it should, but it works. It runs pretty well. So that's how a battery works. Now the electrolytic cell is the opposite of this one. We're gonna make things happen in the direction that they don't wanna happen. And what we do
What
is,
was that called?
that was the galvanic or voltaic cell because it was created by Alexander Volta. Alexander Volta is the one that gave the name volts. Is the one that discovered that electromotive force that ended up, we no longer call it an electromotive force as much, we call it volts because it was named after him, Alexander Volta. So we have another cell, which is the electrolytic cell. In this one, we are gonna push. Water normally flows down, right? If I had a river and you have high energy here and low here, high potential, the water will flow naturally, right? That's what happens in the galvanic cell. You have the zinc, you have the copper, electrons will flow like that naturally. What I'm gonna do with this one is, can I get water up the hill, Anna Kate? No, Kate? Can I get water up the hill?
No.
So how do you get water when you have a house up in a hill?
Pipes.
What do you use to get water up?
Suction.
Pipes, like higher pressure.
Difference in pressure.
But how do I get water? If I have to get water up to a second floor, what do you think people use?
Pipes.
Okay, so I have water here, and I have water there, and I put a pipe. Is
Suction.
it gonna go up?
Or like blowing it. Like the pushing it.
How do I get the
Adhesion.
water up here?
Cohesion.
This is way more basic than you all think.
Vacuum, suction, pressure.
You know this.
Push water up a pipe.
Yeah, but I put a pipe. Okay, so I get that pipe and I put it up. So
You just put a hose to it and it goes.
so I put a hose and the hose will send it up.
Yes.
What
so-
pushes it up the hose?
Pressure.
How?
Air. If there's more pressure, it's gonna push
What puts the pressure?
air.
A suction.
A vacuum.
Is it a pressure valve?
A pump. You gotta have a pump. Pumps water up the hill.
I said pushing it.
Okay, so a pump in this case is going to be a battery. Your battery is gonna have a positive side and it's gonna have a negative, it's gonna have a negative side, right? So what you're gonna do here is now we're gonna have two electrodes that are gonna conduct the electricity. You don't have to have salty water. You could have something like molten salt, which has Na pluses all over the place. Molten salt, it's not liquid. Molten salt is salt that has been pretty much melted, right? So the charges are able to flow. So you have molten salt, and we'll do two of these ones so that you can see it. And what happens is, what is the positive going to attract?
Negatives.
The chloride ions, right? Do chloride ions want to get rid of their electrons?
No.
Not at all. But heck, the battery is gonna rip them off. So the battery is gonna rip the electrons off the chlorides. And what happens when you rip the electrons out of two chlorides? What? It immediately becomes unstable, joins another, and you have chlorine gas coming out of this end, right? And then the negative side is gonna attract what?
Wait, if you take an electron out of chlorine, it's gonna join and become diatomic.
Yes, if you have, because that's a diatomic molecule, it could never be by itself, right?
Okay.
On the other hand, what happens if this attracts the sodium? What's going to happen to the sodium when it gains an electron?
And like one side is gonna make it.
What's going to happen to the sodium when it gains an electron, Emma? It was sodium plus, but now it's going to gain an electron. What's going to happen to it? It was a cation, right? And the cation gained an electron. What happens to it now? What's the charge? Yeah, so it's solid sodium, right? So solid sodium is going to start depositing over here, right? And that's what happens in this particular cell. Now, the cell that Darren talked about did not have a molten salt. It had water. And we're going to do the electrolysis of water, which is lysis means to break apart. That's what you're doing. Using electricity. You're breaking apart using electricity.
Breaking apart what?
Whatever, like in this case, it was the sodium and the chlorine, it took them out. But in water, you're going to have the water. Now, you don't have ions running all around. You do need them. Sometimes you put a little bit of a salt in order to help the electricity move through
Is
this.
this still electrolytic?
Yes. And now, what is the positive side going to attract?
Negatives.
The oxygen, right?
Oh yeah.
The oxygen side, and it's going to rip the electrons out of the oxygen. This is a very basic way of explaining it, but what happens to oxygen when you rip its electrons? It becomes oxygen gas. When you have two oxygens, it becomes oxygen gas. So one side is going to start collecting oxygen gas. And what happens to the other side is going to give the electrons to the hydrogen. Again, this is in very basic terms. There's more to it whenever we actually study this. And what's going to happen to the hydrogen? It's going to become hydrogen gas.
What's that line?
What line?
The red line.
That means the hydrogen gas, you see this is all water, so the hydrogen gas has that much volume compared to oxygen. Why do we have double the volume of hydrogen that we do oxygen?
H2.
You see what happens when you break water apart? You end up with 2 hydrogens per every oxygen. So when we do this cell in class, you're gonna see that this side is gonna be double the volume of that one, because you are having more hydrogen. Maybe hydrogen is smaller, but it's pretty much the same volume as an oxygen. Oxygen is not that humongous.
Wait, what is this whole thing called?
An electrolytic cell.
Can you spell that?
I don't know. We got into a big conversation about this yesterday, because I write it like that.
That's all I want.
That's right.
That looks right.
Electrolytic cell. So I was talking to people because somebody told me that was electrolytic.
No. Well, it's kind of person to person, you know.
And we were talking about words. And you know what happens? Did they tell you about that word?
Words just can be pronounced different ways, Miss Thompson.
Yeah, so when I came here, there is something that we use a lot in Colombia that you also use here. And it was probably created here, but I thought it was created in Colombia. And my mom needed it. And we call it Big Vaporub. And she's like, we need to go to CVS.
You called it what?
So, Big Vaporub. And so we went to CVS. Yes.
Oh, vapor rub?
Yeah. So we went to CVS, and I was like,
Big vapor.
Big vapor.
Big
Ah.
Vaporub. And I went to CVS, and I'm like, I need Big Vaporub. And the guy's like, what? And I'm like, Big Vaporub. And the guy's like, I don't get it. I'm like, Mom, I don't know. What, Big Vapor Rub? And she's like, oh! And I'm like, what? What is that? That doesn't even make sense.
Big Babadoop.
Yeah, it's Big Babadoop. If you talk to any Colombian, it's called Big Babadoop, and we all use it all the time. But that has to do with pronunciation to me.
Someone came up to you and was like, I need some Big Babadoop. I'm sorry,
Well,
what?
if you tell anybody in Colombia that it's called Big Vapor Rub, they're gonna laugh at you because it sounds weird.
Vicks Vapor Rub?
Yeah, what the heck? No.
Big
I was literally making fun of myself by trying to make it sound English, and I'm like, well, maybe Big Vapor Rub, and he's like, oh, and I'm like, oh, that's ridiculous. Can't believe it's called that. So yeah, things is all about pronunciation. Oh, my husband's had a field day with that one.
So it doesn't have to be O2 and H2. It's gonna be like Cl and Na plus. Like
So you're breaking something and you are forcing, you're normally oxygen wants to gain electrons. You are ripping them out of the one that is more negative and you're putting them on the one that is more positive in an electrolytic cell. So it could be something like sodium chloride.
We started with sodium chloride.
We started with sodium and chloride, and then I said Darren actually used water, and the electrolysis of water is something that is well known. So we had two electrolytic cells, one with a solid and one with a liquid. But electrolysis of water is very popular, right? So the other one is too, that's how you plate things. Like if you have a silver plated something, or if you have you do it by forcing the metal to plate wherever it doesn't want to do it. Let me see what else we have in here.
But the electrolytic cell, is that electrolysis?
Electrolysis.
Is that
Yes.
an electrolytic cell?
Yes.
How long are we gonna have to work on the mastering chemistry?
As soon as we're done with this. So as soon as you tell me that you're done, you can start working on mastering chemistry.
Wait, as soon as we're done with what?
With this.
I would like to do that.
I mean,
So if you want to go, do you have videos on this? I have their videos, but if you want me to explain it, I will. But if you don't, then you have time to work.
Is there more on it than we've looked over?
So we have, I was looking to the other things, we have corrosion, but half reactions with corrosion.
What do we have to know for corrosion?
Like if I give you an equation, you should be able to do the half reactions.
What? Can you go over that?
We've never talked about that before.
Never
Yeah, the
talked
half
about that.
reactions, like the something plus 2e.
Plus 2 electrons.
Oh, it's
minus-
just a half
Oh,
reaction.
yeah,
Okay.
yeah. We've done that. Now, there is one question that is gonna be there, and people didn't really do that bad. I was grading the sample quizzes the other day, but you're gonna have the eggshell nonsense again. That's gonna be one question. It's
Bruh.
gonna be.
Miss Thompson,
Because
that's
I want
not
the whole
what
what's the
class
point?
together. Because
I'm never gonna use that.
yeah, the particle diagrams and the net ionic equation, which means the acid is gonna stay together, the weak acid is gonna stay together. And we also have,
You should send that whole note to me in a text.
that's it, I think, you all have access to these.
Was it tomorrow or is it next class?
Did you
Or
end
this
this
video
class
class?
is
So I think tomorrow I'm
Thank you.
going to, I see you tomorrow. Yeah, I see everybody tomorrow.
Yeah, we can't do it
If I'm
tomorrow.
able to, I would like to actually have a lab with these things, because I keep talking about all these things, to have something to do molecular geometry and practice Lewis dots, right? Because I think we need practice on that.